Okay, welcome back. Let me, if I can make it closer. Okay, we were at this important thing, and I want to quickly recap because uh, one thing I'll say, the normal calculation forms are good, which is good. That's one of the more useful applications. So you really need to know your way around. But I want to talk about this result that we stopped with last time. So there are many nuances here which I want to get out of the way. If you take a look at what I've just returned to you, there were some small slips in the things that you proved. So I want to show formally once and for all. How do you show these things rigorously and correctly? Okay. If you are trying to show that the expected value of a sum of random variables is what I say it is, you do it this way. So because I think some of you could not apply this. Okay, let's talk about this first. Okay, I think everyone is in agreement with the expected value part. That's quite easy to understand. Variance has only one twist. You need independence to split it up like that. Okay, how did you apply this to a mean? So first of all, I asked you to show that the mean of x, the mean, the I wonder whether there's anyone in the class that's confused about what this even means. What do you mean by the expected value of a? Isn't this already a mean? Yes, but because I remember how confused I was when I actually, unfortunately, in Malaysia, we learn these things in high school, which I think is not actually a very good idea. Because I think you get a lot of preconceived notions and it's not good. So I remember being very confused about this in high school. Like, isn't X bar already a mean? What do you mean by mean of a mean? It means, if you want to think of it this way, every time you see an expected value, it just means what's the long run behavior? This means the X bar with a capital X contrast to an X bar with a little x. The little X bar means I got a sample mean, and I'm happy with that. That's one. Capital X bar means that mean that you collect is also random. And I gave you the illustration. Every day you go out to hope, get a sample of people and get their mean height. If you keep doing that every day, don't you get a whole sequence of means? And that's what and are they all the same? No. And so this is the random variable that represents the random means that you can get when you go collect many, many, many means. And in the long run, the mean of those random means is the mean of the distribution over which you take, which makes sense. You will sample from the same population, get different means. But in the long run, the average value of all your random means will be equal to the mean of that population. So how do we show this? So first of all, we establish that we know this should be mu. Okay? How do we show this? So you can use the fact that X bar is defined this way. Isn't X bar, you take your first observation, you take your next observation, all the way to your nth observation, assuming that your mean is of size, sample is of size n. And how do you find the mean? You add up and divide by the number of things that you added together, so n, like that. So what I was hoping you'd be able to see is that you can replace all the A1, A2, AN with what? 1 over n. Isn't this 1 over nx1 plus 1 over nx2 plus 1 over nx? All the constants turned out to be the same. So actually, I proved a very, very general form, which you didn't even need. This is a specific application of this. So if you used 1 over n for everything, what do you get? According to this, it means you have 1 over n ex1, and you keep doing this all the way till you reach the last one. Okay, that's what you have. Agreed? Now, This is where you use the thing that we tell you. If all these x1s, xi's all come from the same distribution, then they all share the same mean. In other words, you have mu, 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 like that. So how many mu's do you have? N of them. So this means you have 1 over n multiplied by n mu. You have n mu's. Now again, you can only do this if you know that they are all the same. The means are all the same. I'm writing this out clearly because there is some confusion in the class, because I saw some of you writing mu's inside here. The E this is mu. The mu thing only comes when you have written these expected values separately like that. So I corrected every one of you that made this error. I did correct it. So take a look. The stage to start writing mu is here. Not here. Don't say this is E mu plus mu plus mu plus mu. Yes, numerically it is correct. But conceptually it's wrong. The mu thing only appears because mu is EX1. So don't write mu here, mu here, mu here. Yes, numerically it is the same. But conceptually it's not correct. All right? So this gives you the proof for this one. So is it clear now how you should do the thing properly for the variance? Most of you tripped up when it came to the variance. How do you show the variance? So to save us some time, I am just going to write it like that. The variance of the mean, the variance of x bar is the variance of that. Okay. What have you learned about variances? First of all, you can split up variances if you have what? Independence. Very good. So I'm going to highlight that here. I can't. Can I do a superscript? Never mind. Yeah. What is it? Control. Oh, thank you. Well, see, you're better at Google Docs. I'm not a Google Doc person. I actually don't quite like it, but it's a necessary evil. So anyway, we have this. True independence, we have this. What's the rule? What happens to constants when you take them out of variances? You need to square them. Remember that. So this has to be squared. I'm going to do that thing I just learned. Isn't that nice? Oh, very good. Okay. And of course, don't write E. This is var. Var, var, var. And you're almost done with the proof. Why? And again, some of you wrote sigma square inside here. I don't do that. That's actually wrong. That's why even numerically equal, that's wrong. You know why? The variance of constants is 0. Constants don't vary. This is the right way to split it up. Don't panic, just do it slowly. So you have this. Again, are we told that they all come from the same distribution and they all have the same sigma? Yes. So how many copies of sigma squared do you have? N of them. I want to make sure that you all are very, very comfortable and able to write this thing carefully. And I forgot my square, didn't I? Okay, and so this is still here. I'll erase this. And that is why the answer is sigma square over that is why it's sigma square. I'm highlighting this because this is one of the bedrock principles. If you leave a probability class and not know how to do this, that's not good. So that is why. Okay, so this is always true for any distribution. Do you see the word normal at all? No. These things that you have proven are very general. Now I'll go to the normal story. Okay. So if you go back to your notes, we talked about it, some important results. If x1 is normal, here I am giving myself the license that they might even have different means, u1, u2, and all that. Variances also potentially different. But If these are independent, this linear combination is also normal. It has a mean sequence. It has a mean that follows a sequence that makes sense. And it has a variance that follows a sequence. And this one you can prove. Part of it you can prove by looking at the very general thing that I showed you. Notice the word normal does not appear here. So when you see a result like this, I'm only showing you why the mean of this sequence is this and why the variance of this sequence is this. I have not shown you why this is true. Why is it normal as well? That is beyond the scope of the problem. So I'm trying to highlight the different assumptions, the different hypotheses, the things that you're saying about the problem. And I'm telling you exactly what you can prove and what you not. But this is true. Then, result number 2, specifically, if x1 to xn are independent and of the same, see, now we are imposing something else. If they all came from the same distribution, this is exactly like if n Hope students all coming from Hope College, they all share the same distribution for height. Again, I hope you can see that this is a specific case of this. With what? All the mu1, mu2, mu_n are all the same. They're all mu. All the sigma 1, sigma 2, sigma n are all the same. They're all sigma. And you see, they're all independent. So this, you can write in, this is a specifically, this is a specific case of this. And didn't I show you that the expected value of a mean is mu and the expected value is sigma square over n? See, again, but I did not show you the normal part. That remains unproven. It's like those shows on TV, cold case, right? 35-year-old case never solved. Right? This will be hanging in your mind. I never proved this to you because I cannot. You need more machinery than you have, and I can't prove it. But I did what I can. I proved to you that the mean is mu and the variance is sigma square over n. I did do that. But the normality I cannot prove. All right. Now, now to add to it, we do point number 3. I am going to introduce to you, if you have not heard it before. Actually, how many of you have heard the phrase central limit theorem before this one? Okay, excellent. Well, here it is again. The central limit theorem is the most important theorem in probability theory. And it comes right at the end of probability theory class. Okay? What does it say? It said, and why do I say of all central limit theorems, why there are other CLTs? But they are all much more difficult and involve loosening certain conditions. In other words, you see, there are quite a few hypotheses in the original CLT. If x1 to xn are independent, that's a big one. So people have developed CLTs, and it's an active area of research. If you ever do a PhD in probability theory, first of all, you need to tell me if that ever happens to you. And number 2, you will be probably doing this kind of exploring different CLTs where if I take this away, what kind of CLT do I have? If I take this, basically mathematical research is always trying to, do I need that hypothesis? Can I take that away? If I take it away, will my block of Jenga bricks drop down? Things like that. How much can I get away with removing this? This is a very strong assumption. Independence, same distribution, with mean and variance this, then. And here's the wonderful result of the most famous CLT, which is the simplest one, which I'm introducing to you. Then the mean is approximately normal if n is large. And when I say large, typically 30 is enough. Notice how broad and powerful this statement is. Although x1 to xn need not necessarily be normal, the mean behaves like a norm. This is the beautiful part. That's why the normal distribution is held in such pride of place because of this very powerful theory. Fantastic. We don't even need to know how the parents behave. Their children will form the mean will always be normal. The parent distribution can be anything. Notice, though, if the parent distribution is not normal, then X bar is only approximately normal. Whereas here, if the parents are normal, then X bar is exactly normal. Did you see that? These are all very, very nuanced things you must notice. This is like a this not like this is a mathematical document. Every statement is there for a reason. If I tell you that your parents are normal and independent, then the mean is exactly normal. However, if the parents come from the same distribution that's not necessarily normal, X bar will be only approximately normal. And that approximation gets better and better as your n gets larger and larger. The basis of this, why is this so useful, is this becomes the key to solving a whole bunch of things that people want to know. I have a mean that came from, I don't know, I don't even know what the parent population, but I can say stuff about how likely am I to see that kind of mean. So let's look at an example right now. All right. I want to talk about, let's see. And by the way, this is actually the basis for why that, remember I taught you that normal approximation to the binomial thing. The central limit theorem is actually why this is allowed to happen. I know you don't see a mean here and all that, but you can rewrite this problem as a mean problem, and then the proof will show you're actually using a CLT. So example one, the normal approximation to the binomial has its roots in the CLT. All right, that's why a binomial can pretend to be a normal. Okay, let's do example 183. Yes, okay. So this one is not CLT yet. We don't need the CLT here. You know why? Assume that the weights of individuals are independent. Now notice, and normally distributed. See, the parent distribution is normal here. What I'm going to tell you is this problem can be successfully done even if you didn't know that the people's weights were normal, because you're going to be dealing with a mean. So the weights of people are normal and all that. With a mean of 160, see, they come from a distribution whose mean is 160 and an SD of 30. Now, suppose that 25 people squeeze into an elevator designed to hold 4,300 pounds. I don't know whether you're like me. Actually, I hope not, because I'm quite nerdy, So when I'm in an elevator, you know what I look at? I actually see the state of Michigan inspection, how much weight. I don't know whether you've ever noticed it. It's in every elevator, actually. So, but the thing is, I can't remember now. But this, I think, is a realistic limit. You will see in some elevators. So they have actually judged that the elevator is safe as long as, and they know people can't count. So they usually try to tell how many persons, assuming that people have a certain distribution of weight. But people can count people, how many people are in an elevator. Okay. What is the probability that the load exceeds the design limit? Okay, how do we do that? So write some notation like what I've done. Let me zoom in. Notice I've introduced a new random variable called y. Y adds up all the weights of the 25 people. X1 is the weight of the first person, and so on. Now, do you agree with this statement? EY is 25 EX. If you want, you can say EXI. That's correct. Isn't it? Because Y is the sum of 25 random variables. EY is EX1 plus EX2 all the way to EX25. So you have 25 copies. And how do I know that they're all the same? Because we told you so. That every one of these people comes from the same distribution. They share the same mean of 160. And it should make intuitive sense. If you add up the weights of 25 people, the average in the long run will be how many people did you add together and multiply by the average weight of 1? Okay. See? So now, how do I know y also is normal? Because I just told you in point 16 dash 1 or whatever, I I told you that the normal distribution behaves this way. If you have a constituent of 25 normal distribution variables, all independent, the sum of them is still normal. I'm not using the CLT here. This is not CLT. There's no mean yet. There's no mean at all. So why has this mean? Do you agree? This is where things get tricky. Why is the variance 25 the variance of x? Is it clear why? Var y is var this. But are we told that these people are independent? Yes. Can you split up variances of independent people? Yes. How many copies do you have? 25 copies of the variances. Now, at this point, I really want to ask this question. What would have been wrong for me to do if I had done it this way? This is a classic mistake that people make, and I have to point it out to the class. Why can't I define a variable, to keep things straight? Instead of saying x1 plus x2, okay, see, the correct way to do the problem is what I have showed you. Okay. Did you think about, some people think that it's actually okay to do the problem this way. Can someone tell me why this would not be accurate? This is a quick and easy way, but it's not the best way. Yes. Yes. That's such a good probabilistic way of looking at it. Let's look at it the physical way. This is not correct. What are you doing? You're taking one person and multiplying that person's weight by 25. I mean, in a pinch, you could do that, and the consequences of this are only seen later. Now, Sydney is talking about the variance. Notice she didn't talk about the mean. You know what? Let to be very precise, I'm going to call this something else. No, actually, Z is a bad choice because Z is a standardized PW. All right. Now, do you agree? I've proven to you EY is 25 times, and what did we say? Everyone was 160. Do you agree that EW is also 25 times 165? Isn't that correct? Because we have learned that constants just come out of an expected value, just a square them. But look at the implications of what the variances will be. We have shown you in the slides that we have 25 copies of the variances of the weight. Now, everyone's variance is the same. I can't remember now. What is the standard deviation? Was it 30? Oh, yes. So that makes the variance 900, right? Okay. But can someone tell me, and actually Sydney already alluded to this, the variance of W would be what? Hmm. If you look at the way W is defined, the 25 will need to be squared. And so you have 25, and I'm going to do the control dot. And then you multiply this by 500 because each person's variance is. Now this is much larger than this. And this is why this approach is wrong. I actually had a colleague, a professor, honestly, who he didn't fight with me, but he couldn't see the implications of this. This is the wrong way of approaching the problem. It's a way because it's not unreasonable to think that, okay, let's take the weight of one person, multiply by 25. We're trying to find limits of weight that can go into an elevator. But doing this has unintended consequences. You get much higher variance, not a good idea. See? So that's why I spent quite a bit of time explaining this very, very carefully. So remember, because this is a common mistake, which I have actually seen. So anyway, I think we are back to this problem. So the correct variance is actually just 25 times 900, not 25 square times 900. Because of the definition, and this is why it's so important to write things carefully. This is not the same thing as 25x. 25x just means take one person, multiply the person's weight by 25. This is 25 random people's weights added together. They are different. Although their means are the same in the long run. So the desired probability now is, this is simple. You want to know what is the probability that these people's weights exceeds the elevator's specification. All right. And you just standardize and do the same old thing. See, I found the distribution of y. And of course, this problem I think was conveniently constructed. So these are nice numbers and you can get the answer from the normal distribution table. That means there's only a almost, well, 2% chance of this happening. Whereas if you had done the problem the wrong way, this probability would have been much, much larger because the variability of people's weights is high. The mean varies less. What design limit is exceeded by 25 occupants with probability 0.001? So again, I'm just putting this problem here to throw it in to show you that this is again a quantile problem. Now we want to find what the weight, total weight should be, so that there's only a 0.1% chance of you breaking the elevator. Okay, if you want to think of it that way. So, yeah, so we have this. So we know once again that what we want to solve is this. We want to now find what this weight is that's only exceeded 0.1% of the time. So take your time. I notice some of you, when you do your work, you're a little bit, not sure what's the word for it, unsure how to write things properly. So I see a lot of statements which I know you know what you're doing, but you can't seem to express yourself. So this is what you should say. I want to find this number so that this is like it's kind of like is English grammar taught in schools? It is. It's good because I think there was a time where they actually stopped teaching grammar or something like that because they feel that when you speak a language as your first language, in other words, you can speak the language, but you can't tell me why what you say is correct or grammatical. It's a little bit like what I see some of you doing when you do your normal distribution. You kind of know what you're doing, but you don't write it in a grammatically correct way or something like that. This is how you do it. So I want to know what this number is so that this probability is only 0.1%. And so this immediately standardize. And once you are in standardized mode, then you can consult that SOA additional part I told you where they tell you what the quantile is. Do they offer 99.9%? Let me see. I've updated our class table to reflect the one that I introduced the last time. Let me just check. Let me see whether they have this percentage point. I believe they do. Let me see. Oh, they don't. I wasn't correct. They don't. They only have 99.5%. They don't have 99.5%. Well, that doesn't matter. There's no be a number. So when you don't have that benefit, then you have to do it the old-fashioned way and look for 0.999 inside here. So See, 999 first happens where? Here. 999 happens here. And that is 3.08 or something like that. So if you go back to our slide, 3.08, 3.09. Solve for x. And again, do a sanity check. Does this kind of number make sense? Yes. The total weight, if it exceeds, if your total, the probability is 0.1% of exceeding. In other words, you need to have a threshold weight of total weight of 4,463 pounds. That is the threshold that's hit only 0.1% of it. Is this okay? I've not used the CLT. There was no need for the CLT. Why? Because you know that the people's weights are. And I believe the next example will not be like that. The next example doesn't say that. Yeah, see? Okay, so in a men's basketball league, the standard deviation of the player's height is 2 inches. A random group of 25 players is selected and their heights are measured. Estimate the probability that the average height of the players in this sample is within 1 inch of the conference average height. Okay, notice the word normal doesn't appear, which means you are going to have to use the CLT1. This is a question involving the average height. So, how do you approach this problem? Immediately appeal to the CLT. We know from the CLT that the means of a sample, I want to know, did you all know that when you say random sample, you're actually saying that everyone in the sample was independent? You're saying it in another way. So what you're basically saying, random sample is, this is, random sample is actually saying that everyone in the sample is independent. Okay. So X bar, approximately normal, mean mu, variance is, see, this standard deviation is for every player. Sigma is 2, sigma square is 4. Remember the rule? Sigma square over n. Today, I'll open up a homework, and it's not a long one because it's the last homework. And it will all be about a normal distribution in CLT, so you get more practice. It's a short homework. I mean, there's quite a few questions, but they're all very short. All right, so to give you more practice with this one. So you have mu and 2 squared over 25, sigma squared over n. And so what do we want? You want to answer this question. What is the probability that the average height of the players is within 1 inch of the average height? This is saying in words what this is saying symbolically. Within 1 inch. When you are within 1 inch, you could go either way. You could be anything from -1 to 1, which of course is. I don't know how your mind works. If you don't like this kind of thing, this is perfectly fine. If your mind works this way, then that will be correct. And is this an easy problem to proceed with? Standardize. We already have X bar. We know from the CLT that X bar has the mean mu. Half the journey is already there. You've already standardized. So all you need to do to turn this into Z, you divide by the standard deviation of the quantity that you are standardizing, not individual players. The focus now has become X bar. And we know X bar has this as its variance. When you standardize anything, you always divide by the standard deviation of the thing you are standardizing, not of the constituents. So there are many places you can slip here. Be very, very clear. I'll say this again. The players themselves come from a distribution where the standard deviation is 2. But this CLT tells us that, okay, if the constituents have a standard deviation of 2, then as a whole, the mean has this as its variance. See, the sample size is involved, which makes sense. Because the larger your sample size, the less variable your mean becomes. This should totally be in the formula. Samples are not created equal. A sample that's large is less variable than a sample that is small, and that's reflected in the value. And so standardize based on the variable that you are looking at here, not the constituents. And then you have this, and then the rest is just looking at the paper. Is this okay? I think I have another example of CLT which is coming up. Let's see. Yes, I do. I want you to do this as an ICP. All right, do example 185 as an ICP. Notice, what do I say? Xi come from an exponential distribution. Do we care? No, the CLT bulldozes through all these things. Your parent distribution can be anything, but it enables you to answer probability questions about X bar. So I want you to give this a try. All right, give this a try. See if you can do this one. All right. Anyone know why I'm telling you this? I need to tell you this because from this, can you derive the mean and variance of the parents? You need that. The central limit theorem needs to know what the mean and variance are of the parents. These 100 parents here. That's important. Once you have that, you can write a statement about the CLT. X bar is approximately and all that stuff. Give it a try. Any problems out? One thing to point out, you know that these, if they were normal, then the mean would be perfectly normal. This doesn't carry to other distributions. An exponentially distributed parent doesn't yield an x bar that's exponential. That's why you need a CLT. Yes, if these were all normal, x bar would be normal and would be easily solved. But these are not normal. These are exponential, yet x bar behaves like a normal. Yes. Okay. So the most of these expected but but you know, oh, okay, so you have this, yes, no, a little bit. You are actually saying, this is the means of one, let's say, this is the means of one person. Because for this potential, the base is order of the square, right? That will be 1 minute. That's right. But that's what does the CLT say? The CLT says, so the CLT says that X bar is approximately sigma square. And what sigma square is? Sigma square is the variance of the population from which is the. In other words, what is sigma square? What is the variance of the individual from this system? So don't write that here because variance of X is what it is. That's it. So where does that dividing by 100 happen?
So it should happen.
Yes, that's right.
Okay.
And I think you're okay.
So now I think you're more on top of it. Yeah.
No, this was.
I'm pretty sure this is.
No, that's right.
That's about it.
Yes.
Like, just fine. It's just about it.
So I'm looking to see multiply it by.
To the square root
of the
variance.
So, first of all, establish if all your constituents are then it's So you need to establish what is in there. So you would have the for an exponential, which in this case, so what is, yes, so the variance, so to be very, very careful, you should have this R X, not X, the variance of X is. It's just one. When you thought this is an R, then you, I saw that nice picture. So what does it say? When you get X bar is approximately, once you know the continuity, the X bar is approximately, it shares the same meaning as all the but what's the meaning? So what is here? It says what X bar is.
At 0.05,
Yes. The reading from this order, which is actually, I think, very good.
but over here,
So let's enter the six over.
we know that there's
Just which means when you stabilize how it is.
so.
Was one answer please. Now you're seeing. Oh, right. This is
1 minus.
Also extended sides. Subtract. Also, I think. That's what I was saying.
So wait,
I don't know. When you divide the
this
SC of
point
the
four happening here.
square.
There. So
That's fine. Everything falls back.
because it's like, oh, we're saying according to the people, but then we have to take it off what's both. So then we just are left with sandwich. That should be. Oh.
So then.
Actually. Okay, so the probability that it's between that.
I will give you the final answer.
Okay.
Okay, that's the final answer.
Right.
So just see if you can work until you get there, alright?
Right.
So,
Oh, okay.
okay. So there's, you know what? It's already here.
Oh.
But for this one, we have to subtract. Yeah. Because when you standardize, you subtract the E, you have to stop the see? This is in this basketball example. So the question over is started to the goal of separating. Yeah.
You said. Yeah. So we're gonna take up 2 zeros. 1, 2, 3, 4. So then we're left with 1, 2, 4. Also no that equals this. And this is 100.
Yeah.
So then you multiply that on.
So
So we have 1 million equals that. And so we square that.
this is correct. 10%. So we square root of this. You don't square root this. When you standardize a thing, you always divide by the SB.
So we are no longer following this.
That's right.
Now we are.
That is why this is very key. Writing the distribution of X bar is very key.
Because now we're
Oh,
approximating.
you forgot your pen. No.
Well, 100 is just what this is.
This is just saying approximately.
So then that is.
And what is the square root of 10,000? Not a nice number.
No.
No, it is a nice number. It's 100. It's
I
100.
was just gonna say.
It is. No.
Yeah. So they should change everything.
It should. Yeah, I think it will.
Is it just, we just move the decimal
Yeah,
over
just
along?
so it's 0.5.
Oh, yeah. Oh, okay, so one minus. So now the sandwich is changed. Okay, right. Yeah. Wait, hold on. No.
No.
But that's just the first layer. What if you set it back?
Right.
It should just.
And that's what we got it.
Okay, so now we just have to.
Right. See, we were cooking the right thing.
Right, but then he was just
So, yeah, that's the danger of when you look at a formula, we say x minus mu over sigma. It means basically, in words, it is subtract the mean of the thing you are standardizing divided by the SE of the thing you are standardizing.
which we're not standardizing over just a pure and more.
No, it is not standardizing a mean. Good. Okay, I want to discuss example 186 with the class. I want you to do it as well, but I will start you off. Look at example 186. An insurance company issues 1,250 insurance policies. Notice the large number. It is to make all approaches non-CLP. It's basically just go away. Right? You're not going to do it without CLP. So there's 1,250 policies. Now the number of claims filed, see, the number of claims filed per policy holder. That means how many policy holders are we going to be considering? 1,250 of them. The number of claims that they will file is Poisson with a mean of 2, which makes sense. In a year, in the long run, a policyholder will file 2 claims. Okay. Assume that the number of claims filed is independent. Why do I have to tell you that? If I don't tell you that, you can't use the CLP. Okay? What is the approximate probability that there is a total of between 2,450 and 2,600 claims in a 1-year period? Okay, how do you solve this problem? Always start off with the basics. You know this is going to be a summation problem, but you don't add up to 25. Anybody care to tell me what should I add it up to? How do I modify this? Yes, you add up to, and can someone, it's always very good to be very precise. What is xi? Anyone care to define what xi is? Tell me precisely what you are adding. The I represents good. The I represents policyholder I. But what about policyholder I are you interested in? You can't add people, okay? People aren't numbers. But what about the I person? Yes. But what about the claims? It's something to do with the claim. A claim is also. I'm harping on this because this is important. What is XI? It's something claims of policyholder I. Can you be very precise? What about, it's not a claim, you can't add a claim because a claim is actually a size of claim. Are we interested in the size of the claim or what? What is XI pertaining to policyholder? The number of claims. That's why this is modeled as a Poisson. Notice we are not modeling the size of the claim. That's not what this problem is interested in. How many claims did you make? Or did I make? Okay. Now we are told, see, I'm giving you this example because I'm trying to show you that these central limit theorem-like problems are disguised in many ways. Okay, we are told the distribution of the number of claims that someone makes. It is Poisson. What's the lambda parameter here? What's the average number of claims that a person will make? 2. So we know that xi is Poisson 2. Can someone tell me, if I tell you that this is Poisson 2, is it clear that the expected value is 2? That's what I've told you that, okay? What's the variance, though, of xi? If you know the behavior of a Poisson, you should be able to tell me this answer. Yes, also 2. Good. So now we return to the question. What is the question asking for? What is the probability? Always read the question. What is the probability that there are a total of between this number of claims and this number of claims in a 1-year period? So can anyone tell me what mathematical statement do I want to find the probability for? Anyone? Help me fill in this parenthesis. We want the probability of what? Use the notation that I've introduced here. To give you a hint, it's an inequality statement. What is it? We want to know the probability of what? Yes. Yes. So what you want is actually this. I'm going to save myself some time. I think this is going to carry to this document. Let's see. You're very good. Okay. Between this, in other words, what you want is, I hope you can see this. So I want you to really look at this. See how I broke the problem up slowly. First of all, what was I interested in? I want to know the total number of claims. I know an individual on average only makes 2 claims a year. And the claim distribution is Poisson, which then tells me this. You see, you get this from knowing this, you know. I didn't tell you this. That's why we introduced the Poisson first. The Poisson is such that if you know the mean, you know the variance. Okay? Then write down, okay, what did I actually want to answer? And this is where the power of the CLT is going to come in. This issue is, I want to know this. Now, before you start yelling at me and say that, I don't see a mean here. Yeah, I don't. But can you turn this into a mean problem? What do you need to do? This problem is multi-layered. Okay? That's why I'm taking it slowly. This is not a mean. But how do you turn this into a mean? Is there some magical thing you could do to this inequality that would introduce a mean? You know, some people, they can turn, I mean, to be frank, some people are very political. They will find politics in anything. I've met such people that are very unpleasant to talk to. You have an innocent thing like yeah, I was talking, I'll give it what happened. I was talking about, oh, I need to renew my driver's license in years that end with 5 or 0. And this person said, oh, there's a presidential election in 2020 or something like that. How did you go from there to this? In other words, politics is so in their mind all the time. They see politics in a driver's license, a date of expiration. That's how, and you know, the Bible says, you know, out of the overflow of the heart, the mouth speaks. So in other words, what you say reflects what's in your head. So I guess I speak so much of probability that shows what's in my head. Anyway, so the point is, this is what you want. There's no mean here, but can I make sure a mean appears in how How do I inject politics into this? How do I make this into a mean statement? Anyone? Yes. Divide by 1,250. Why? If I take this and divide, okay, so this is this. Divide everything by 150. If I do this, I have successfully. Oh, sorry. I think I wrote. No, 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 you're right. 1250. Sorry. Got carried away. Yes, yes. Thank you. Yes. Doing this has forced the system to put a mean there where it wasn't there. That's why totals don't scare us. Totals become means in such an easy way. Divide by how many things you added up. You can mean the thing. Okay, so this is equivalent to this. Now, why are we so excited that this has turned into a mean problem? Because don't we have a very precious thing called the CLT that enables you to approximate how means behave? Can you take it from here? Because I have made the problem back to the problem that you have just started. So if this is confusing you, you okay, I know I should not call this y bar. I should actually call this x bar. You know why? Because y was built up of x's, and so we tend to call y over 1250 is x bar. All right. This has become a problem of order, and you have just solved CLT problem with means and all that. So you know the constituent distributions. And again, I'll give you the final answer so that you know you're on the right track. Uh, the final answer is 0.8185. See if you can get this. 0.8185.
Oh, okay. So I thought you were like that. She's how the laws. I think one of the third of them. I got it.
So I don't know how to.
Well, that's just. I don't really think. And then.
Oh. So I got close to it. I don't think that's so I did not. One.
Okay. So let's think about this.
Okay.
Is that actually what we're looking at? This album will only.
One second.
So. And people was really weird. And that is weird.
That's scary, but
I think that. No, that's just the other.
okay. So
Right. Like compared to.
that's we're
Right. Okay. So this is probably not right. Our value is -25. Okay.
let me see export. Okay, so we have export with because it follows the meaning of this. And I heard you say something that's actually what is the meaning of that?
That's actually the meaning of X bar. So it is the upper minus because over that it's going to be.
Yes. Not just
Right.
like you know what?
Just two because.
The variance of a croissant
Yeah.
is which is two. So it's already variance two.
Okay.
So if you and what is this? What's the square root of that? What is the square root of 2/125?
Great. We have to see those here.
Yeah, because they use no, yeah. Here you can write 2 over. That's right. That's always taken as a variance. And then when you standardize, it's effectively this divided by not 2. You see?
Right, that was pretty bad when we spent
So you actually divide by
not.
and to get over 1/6 when you square root this is it not a square root.
Wait, so why are we?
Because when you standardize you divide by the x, you not the variance. 0.016 is yes.
Oh, wait, so this.
Don't worry, just ask me. This is 0.0016. This is correct.
Right, that's. But so wait, we're still.
You never standardize by
Okay.
Yeah. So just go with everything.
Right.
Are we okay with this one? Oh, no, okay. Well, let's see. So what it goes through. Okay.
Wait, I got a -1.
Me too.
Okay, hold on.
Share the same.
I did. Oh my God. That's so fun.
So,
Yes. I think it could be nice So
This is.
yes.
I know.
And then it becomes a promo. If I know about somebody you have
Oh.
and then when you standardize, yes, you're correct. You get you know,
For some reason, this class, I switched most of this with most of the other things.
I'm not pleased to know.
Right. I have to.
Yeah, yes, you are listening to us.
That's okay.
It's the small
You standardize, you don't.
Yeah.
So there are many things very, very valuable. First of all, what is one perception and what is expression?
Well,
Yeah. It's like, yeah. It's hard to skip.
no, I'm just like,
I'm pretty sure.
I should swear to other exams, so I don't think. I hope so, because those are my 3 exams. So those are 35, so there's no lie, so.
No, I think that's okay.
I think this is.
Because if you guys would be quite nice.
That's up there. And you're. Yeah. Then this is great.
Yeah. But that's just something that's-
That's what we get people that do it.
Spoiler, yeah. It's the final.
Yes,
So
okay.
that's what I thought it was.
So some of you are asking about the final. Yes, I will send email about this formally and about the cheat sheets and all that. The final, not my choice, registrar's choice. It's unfortunately Friday, 12:30. But I will double triple check before I send it. Yes. Yes, but of course, with more emphasis on civil policies. But it won't be as detailed as those other exams. You still need those things. That's what I was saying. Math is always it's just that the focus was not like so many questions.
Yeah.
I mean, like, look at this one. Maybe you go to Boston. It's very hard to dissect. So I don't think we have time to start. I don't want to start this and then not finish it. This will be our last example, believe it or not. So next class we will, yes, because there's only 190, and we are not going to do the gamma distribution model. So yes, so this will be the last example. We will keep it for next time. It's a difficult one. I'll tell you, no, it's a very good one, but it's challenging. Yeah, if you can think carefully about it, is along the lines of this eye vision care policy thing. It is something similar, but it has a twist. because you see there's a code. Okay, but it is also a CLT problem. It is also a CLT problem. So next class we'll wrap up by finishing the normal distribution and maybe do a quick review. So I will open a homework tonight. It's all about the normal. Okay, I don't know whether there's any explanation. I don't think so.